Welcome to the Inside EVs podcast and the 6th in a 10-part series of Tech Talks presented by AVL. My name is Martin Lee. There's so much to learn about the exciting and dynamic field of EVs that we wanted to go to a company like AVL. Now, they work across many different areas of electrification and with many other companies who they're all driving towards an electric future. Now, they work with startups, they work with the world's biggest established automakers, and today we're going to play EV war games, if you like. We've decided to launch a brand new EV from a company called Inside EVs Motors. Let's invent that one. So, how do you do it? How quickly can a startup get a vehicle to market? And how can car companies use electrified testing at the cutting edge of technology to make a product? Well, let's find out. Welcome to today's guests. Luigi Giordano is Director of Application Electrification at the Headquarters for Testing Systems. And Nick Birger is the Department Leader of Methodology and Testing at AVL in the UK. Let's start with Nick. How are you doing?
Hello. Doing well. Yep, very nice to be here and looking forward to catching up with you guys.
You are in sunny Coventry or not so sunny?
Beautiful Coventry. I think it's a little overcast here. Rode my bicycle in today and I don't think it's going to rain on the ride home, so any day without rain is a good day.
It's a good day, but how is Graz in Austria? We'd go to Luigi, and how are you?
Yeah, perfect, thank you. Sunny also today in Austria. We had some few days of cold and grey sky, but today is pretty nice.
Well, we can ask for no more. So, let's talk today about electrified testing. We're going to jump straight into this because it's a topic that I imagine many of our listeners haven't necessarily thought about, and yet it's so important when it comes to electrified transport and e-mobility. So, Luigi, we'll start with you, actually. So let's start with a hypothetical question. If I want to start a new car company, we're going to call it, I don't know, Inside EVs Motors. Okay, for want of a better name. If I just want to start this company and go out there to the marketplace and start buying in parts and start making an electric vehicle, how many suppliers are out there to get electric parts compared to if I wanted to start a combustion car business? Like, in other words, how new is this field that we're in?
Yeah, well, definitely it's still a new field in its infancy, that's clear. But if you have the possibility to access to many or few suppliers, depend on the type of vehicle which you want to realize, which you want to bring to the market. So the number of suppliers, if we speak about the conventional passenger car, is definitely there. There are enough of them. There are also some of those suppliers offering a complete platform if you want. This may help you to speed up to be on the market with your vehicle. But on the other side, if you are planning to do, for example, a fuel cell vehicle, there you will have definitely a challenge to find a sufficient number of suppliers. At the same time, you may have a challenge to find sufficient suppliers if you plan to start a larger production for a very cost-attractive vehicle. There definitely you will have a challenge.
Okay, so we'll keep it as simple as possible. We won't make a fuel cell vehicle as our first one. But in my self-appointed role as CEO and only employee of Inside EVs Motors so far, let's start putting the car together. And immediately now I'm thinking about it, this is a pretty daunting task. I mean, there's so many bits of a vehicle that we need to source and put together and test. Nick, can I ask you, how early in the development of this imaginary new vehicle that I'm making today do we start testing?
Yeah, so it's a great question. I think with electric vehicles, we very much transformed the development landscape. And these days, the testing begins very early. Concepts are readily turned into simulation and models and so forth. Stuff like tire models, aerodynamics, all of that is relatively boring physics. When you start having the idea of what your e-motor, what your inverter is going to look like, you maybe work with a few suppliers and you get the simulation of that kind of given to you and you start incorporating it into what is a model of the entire vehicle. So from there, you've got what is the concept, some simulation behind it. And slowly but surely, you can start testing components as they become available. So for example, we've got the entire model for an electric vehicle at the concept stage, and then will be delivered an electric motor for that matter. We'll add the electric motor into a test bed, so it could be an e-axle test bed, and put that into the loop of the model. At the same time, what we're doing is we are removing that element of the model. So in this instance, we take the e-axle simulation out of it, replace it with the real component, and in fact, we just validate our models all the way back. And so before you know it, you can start adding in inverters, you can start adding in various power electronics, up to and including the full vehicle. And at every stage along the way, you are validating, you are ensuring that you do have robust models, and before you know it, you're up to the full vehicle stage. And if you do this properly, you do it as a complete system, once you get to building of a prototype vehicle, you only really need a couple of them. So if you do your work well enough in the early stages, it really saves you a lot of time and money in your entire development process. So these days, as I said, as soon as you have a concept, a lot of the simulation and the modeling is well understood and can be brought into the loop, and then it's just a matter of getting the components and validating everything along the way. So it's really transformed this in this day and age.
I love the idea that we're saving some money here. And just a follow-up question, Nick. So, over the years we've seen different car makers, different OEMs come to market with their first or second, third versions of EVs, and they talk about how they had 100 cars pounding around the Arctic and Africa and hot testing and cold weather and all that kind of stuff. But with modern day electrified testing, are you saying that we don't need to make 100 prototype cars, that I can save a bit of money here?
Well, that's absolutely correct. I mean, the vast majority of your validation routines should all be done on the testbed, where everything is reproducible. We can recreate really any scenarios these days in our development environments. We've got dynos coupled to each wheel, so we've got independent speed and torque control at each wheel. From there, it's very easy to do any scenarios that you can imagine, and ultimately all you need that final prototype or two for is just to make sure that the car, joking aside, doesn't fall apart in the real world. And it's just it's really transformed what our customers are doing. And if you think about how expensive it is for hand built complex prototypes to be put together, that savings alone makes the transformation to these earlier development platforms have a very attractive payback period.
Already we're saving money with Inside EV's motors. This is good. I need to get some more employees on board, though, and I'm guessing I'm going to have to go and advertise for a few jobs, and maybe people will join us who have been up until now making combustion cars, and that'll be their expertise. Luigi, how is testing EV components different to testing combustion cars?
Yeah, well, there are many differences. Of course, if we speak about pure electric cars and fuel cell cars, the first difference is that you don't have emission testing, which is a relevant and time-consuming part on the combustion engine vehicles. On the other side, what you have is that you have a long-lasting battery validation to do. This is one of the first things you actually have to start to test when starting a new vehicle program, because you have to address and to validate the lifetime of the battery. Another key difference is that on electric cars you have a lot of communication between the different components, so the validation is getting definitely complex on having the different inverter, E-Motor battery, charger speaking together and being safe together in the vehicle. This has to be validated and tested. And what also is definitely a key in case of electrified car is to have an increased integration of those components, because you have to increase the efficiency, decrease the weight, reduce the cost. So this means that components tend to merge together, and this is making more complex to validate them. Let's say the procedure is definitely different than in a conventional car. And as Nick already mentioned, of course, simulation is definitely increasing in the complete validation process.
And now, in some ways, EVs are more simple, requiring fewer parts in terms of, if you make a direct comparison to a modern, efficient petrol or diesel engine in terms of the sheer number of parts. But in some ways, I guess they're more complicated as well. So how do we use electrified testing to take all those things into account? Who wants to take this one?
Yeah, I can take that. I mean, you look at electric vehicles, the whole premise there is how beautiful they are in their mechanical simplicity. We're talking orders of magnitudes, less moving parts. But if you think about it, the problem shifts away from being a mechanical one to really a software and control system problem. You think of your modern EV and the ones that are coming up in the next few years here. They're coupled with some of the most complex autonomous driving systems we've seen. Modern EVs these days have 2, 3, even 4 electric motors. So you think about the calibrations that need to be done in the torque vectoring. You look at some of the cool stuff out there, all these tank turns that the EV trucks can do. That all takes new means of development, and that's kind of just in the drivability aspect of it and the ADAS systems. But if we look at the battery side of things, how is the battery life cycle going to balance itself over time? How is the battery going to degrade? What happens if we encounter safety issues and various elements there? So the problem is really shifting away from something that you saw on the combustion side of being a mechanical fluid dynamic type problem to something that is very much software and control systems. And I think it's quite a decent view of what the world is becoming, where everything is kind of becoming how good your software is making it. And that's what we're going to see in the future here, that, I strongly feel we're going to converge on what is an optimum EV architecture, and then it just becomes what and how good the OEM is with their software.
Can you just explain to the listeners what torque vectoring is? Because we hear that phrase. Obviously, there's the trucks, there's vehicles with hub motors. There's the Rimac C2 for those with a couple of $1 million spare. That's got 4 motors, and so that can one motor, one transmission per wheel. We hear that phrase torque vectoring, but what does it really mean?
Well, I mean, let's take an engine, for example. An engine can control the speed and the torque at the output of the at the flywheel. That then gets converted throughout the drivetrain into various torque splits across the vehicle. Here, with an electric vehicle, let's take 4 motors, for example, I've got independent speed and torque control at each wheel. So if I'm, doing off-road drivability and so forth, I can precisely control the torque delivery at each wheel, and that gives me the optimum drivability in off-road conditions. If I'm doing lap time optimizations, for example, you'd like to take an EV around the Nürburgring or wherever, the torque delivery at each wheel around each bend and the optimum delivery of that is going to give you such a better driving experience. And that, these days, especially with modern EVs, that has just opened up a whole world of new possibilities.
Okay, I understand. Right, let's get back to our fictional car company, Inside EV's Motors. We want the customers to be safe, but also the staff who are developing this vehicle to be safe. Now, many EVs kind of float around 400 volts. I mentioned Rimac, they've been using 800-volt systems. Porsche have got a lot of headlines for an Audi as well with their new e-tron GT. That'll be an 800-volt system. I guess EVs can go even higher. Luigi, how do we test for safety?
Yes, so definitely on the passenger car, you're right. The trend is towards the 800-volt. For commercial vehicles, we will have higher voltages. There are norms and standards up to 1,500 volt, so we will come also up to there. And the high voltage is one of the possible risks which you have in the development process. There are other risks. Of course, everybody knows that batteries, if not properly managed, they can burn. You have also very high-speed electrical motors with 20, 30, or maybe higher rotating speed. And all these things are additional risk in comparison to a conventional car. In case of the voltage, the solution is relatively simple. You have on the product itself earth leakage monitor system. This is inside the product by law to protect the user of the vehicle. But also on the testbed you have a similar equipment, of course industrial, in an industrial version in this case, which look at the same high voltage and make sure that there are no leakages. The employees working on prototypes and developing the electric cars, of course, has to go through a specific training because obviously to deal with voltage needs specific protection. Also during the production process, products are validated and checked on this aspect. Yeah. So for what concern other typical risk, which is the battery, there the validation has to be done on all the critical conditions, which can be high temperature, low temperature, high current, and etc., etc. And during the validation process, the control unit of the battery is instructed and parameterized to avoid those critical conditions in a way that then the car on the road is not creating a risk for the user. And last but not least, there are a series of environmental and abuse tests, which by law has to be executed on batteries and electric powertrains, which exactly make sure that the car, in case of an accident or in case of falling in a water, does not create a risk for the people around it.
Yeah, of course. Yeah, I guess the an interesting real-world example that people may have seen in terms of taking safety seriously is if in motor racing, if there is a crash, as different series are electrifying, you'll often see the driver jump off of the car, and the marshals have their safety gear now and rubber gloves, and there's lights on the cars to tell the marshals if the car is safe or not. So
definitely. There are also rules, new norms in in Asian countries which request that the battery must have a certain resistance in time before taking fire, also in case of problems. And this is exactly done in a way that the user, the owner, must be able to leave the car in case of an accident, has enough time to leave the car before the battery takes fire. So the topic is definitely on the agenda. There are tons of norms and changing norms for the transportation of the spare parts, for example, also. And this is, of course, taken very seriously in the development processes of the customers.
Which, of course, reminds me of a previous episode that we made in this series about battery safety, and as you mentioned, in China and regulation, and how there are, particularly the cobalt-free batteries, which are more stable, maybe less energy dense, less performance, but certainly they tick the box for safety. Check out the previous episodes in your podcast feed if you'd like to find out more about the previous shows that we've done. Nick, can I ask you about simulation, just in terms of how close we can get to the real world? Like, obviously, simulation's only as good as the data that you put into it, but we want to make sure that those two things kind of match up as best we possibly can. So how do you simulate those real world conditions?
Well, there's really two ways to do it these days. I mean, you can build your own scenarios using kind of standard libraries where, for example, curvature is known, profiles, so forth like that, and build your own scenarios, or you can actually record real-world data and then replay that in the testbed. So we do both of them. I mean, these days, especially where I work at Technical Center Coventry, we've got 3 pieces of software. So we use VSM, AVL product, pretty extensively. We've got DSpace and MATLAB as well. And I'll give you kind of examples of what you can do today. So one of the most important things we'll do is we'll get real world data where, somebody could be out driving the sandhills in Dubai with a logger on their vehicle that's recording all the various vehicle signals and so forth. And the important ones, it could be acceleration, it could be speed and force at each wheel. All of that is then replayed on the powertrain testbed or chassis dyno, whatever your environment is. And you can replay that maneuver over and over again, and using tools like Cameo, various DOE softwares, you can optimize that one maneuver and give you whether it's you're optimizing for pull away speed, range, performance, all of those sort of things. It's quite intuitive. That's just replaying things, but the big one for us as well is, like I said, we can dream up these scenarios of hypothetically a driver out doing laps on ice, and through a standardized library, GUIs and all that sort of stuff, you can just drag and drop those scenarios, and then they get played back down on the testbed. So ultimately, it comes down to two things. I guess if you're building your own scenarios, again, how good your models are. These days, the software that we use obviously has very well validated models behind it. And at the same time, how good is the integrity from your real world data if you're going down that path as well? So, two ways to do it, and that's something we do daily.
Luigi, when we are applying testing to electrified testing, we want to make sure that obviously we get as accurate as possible. But how accurate can simulations and tests really be?
Let's say that at first, not always high accuracy is requested or required. If you do, for example, durability test, it is not a matter of being very accurate. It is maybe a matter of being accurate every specific times, events where you measure how the component degraded over time, but during the durability test is not such a big issue. Where it gets really important to be accurate is specifically when you improve the efficiency of the powertrain. And there it is typically required to be one order of magnitude better than 1%, because in the end what the OEM, what the manufacturer wants is to be able to certify an electric car with a range, with a high range. And if you think that the range of a modern electric car can be in the 500 kilometers, and when driven in the certified test cycle, this may take 5-6 hours to deplete the battery, you will understand that you need to be more accurate than 1%. You need to be in the range of 0.1% if you really want to improve your components, your powertrain, to achieve higher ranges.
Right, so we're putting together our fictional car company, and we've decided that we need to do as much electrified testing as possible, save money, and get to market as quick as possible. But what are the variables that we're able to actually test for? Not just making sure components last, but other things like performance and actually using the car day to day. Nick, what do you reckon?
Well, perfect. I mean, at Technical Center Coventry, we see this again on a day-to-day basis, and the answer is everything. If it all depends on what the car brand's DNA kind of looks like. If you're going for performance, obviously you're going to look at what your pull-away speeds and performance are over that. That's obviously your 0 to 60 times, that sort of stuff. EV range, again, if you're maybe in the more economic sector in your car, you're going to be doing all the EV range, which inherently means efficiency. How many watt hours per kilometer is the vehicle consuming? Big one these days as well is functional safety. So we can insert failure scenarios into the vehicle, whether it be a short circuit, it could be multiple things, and check the vehicle behavior around those safety criteria. Drivability, as I mentioned, is a big one, especially in off-road scenarios. A lot of our customers will have a whole world of different opportunities if they take their EV outdoors. and there's lots of thermal loading stuff, so how well the coolant system is working, what happens if you're testing very hot scenarios, very cold scenarios. We can even do altitude, where we're basically testing the entire boundary and envelope of that vehicle. So the more you test, the more you learn about the car, and the more you can develop it to be a complete product. So these days, I mean, there's no simple answer. It's everything.
I will also, Nick, if you allow me, I will also add that the electromagnetic compatibility is also a very specific problem on the electric cars. So there is a more extensive testing needed, and noise and vibration. They have a very different pattern in comparison to combustion engine cars. So on that point of view, it may even be more demanding to give a proper sound brand to the vehicle with electric cars.
Absolutely, great point. And especially these days, the sound is going to be so important because it's changed so much compared to a traditional ICE that you're absolutely right there. That's so important.
Let's talk a little bit about, my knowledge is pretty superficial, but I do understand that my house runs on AC, and I understand that my lithium-ion batteries store DC, and I get that motors can be AC motors as well, so at some point there has to be a conversion. I understand there's an inverter in the vehicle, and in our fictional car company, Inside EV's Motors, we know the inverter is going to be really at the kind of the core of the vehicle. So tell us a little bit more about how we test that, because we want longevity, we want high performance, we want to charge nice and quickly, but also we want to do this and save money as well. So Nick, tell us about inverters.
Well, the inverter is the heart of the electric vehicle. I mean, it's what is taking the DC current that comes out of the battery, translates it into three-phase AC, and ultimately that frequency that you can adjust it to controls the performance of the e-motor. So really it is the heart of the power electronics and the control system behind everything, and ultimately how well you tune that component gives you all the behavior of the electric vehicle. So when I'm slamming down on the throttle, that signal is ultimately translating into how the outputs are on from the inverter into the e-motor, and it's so important. Also, with the inverter, it's important to note that these days, with EVs, when we're braking, we can actually use the e-motor as an alternator and regen and harness some of that energy back. So that what that does is converts three-phase back into DC and has it go the other way. So ultimately, it's as I mentioned, it's the heart of the EV, and it's so important that we tune that right, we calibrate it right, and that affects everything down the chain in the EV.
Even before we've kind of made our motor, though, or bought our motor in from a supplier, can we emulate that in terms of just get that inverter right first? Luigi, can we do that?
Yes, this is definitely the right approach, and it is done in this way. It is done with emulation on both sides of the battery and on the side of the electrical motor, because of course, if you can avoid to have a real battery, you have more freedom to simulate and parametrize the condition on the input of the inverter. And there, to replace the battery, you basically take a high dynamic power unit with a real-time controller which simulate the state of charge, the temperature of the battery, and so on. This is on the DC side. On the AC side, we do basically the same. We need an even more dynamic power unit, which is simulating the oscillating voltages and currents, plus the speed signal of the e-motor. And by having these two pieces of hardware simulating battery and e-motor, we can, of course, bring the inverter to all the real condition which will happen in the real car, but in a very compact, efficient, and flexible test environment. Because, of course, if you can emulate, you can link the emulation to a computer. The computer can change this behavior, this emulation, during automatic test profiles, and you can really be independent of the mechanical modification which are not existing because the electrical motor is virtual in this case.
So not just the E-motor though, but every part of the EV, so the battery, etc. So even without attaching it, we can simulate all of those parts coming together? Exactly
in this way, yes. So as I said, you can of course start your simulation by having very simple models on the battery on the E-motor side, but once you develop your basic control modes inside the inverter, you can make the further step and add the model of all the mechanical components of the powertrain, add the models of the tires, of the asphalt, the model of the driver, and the traffic if you want, and so on and so on. And basically having a testbed just one single piece of hardware, which is the inverter, and all the rest is emulated with fast, real-time controllers acting on these power units. Whereas the challenge in this case is, of course, more you go in the complete simulation, more you need accurate parameterization to those simulated models. And this can be done in different ways. One of the solutions is also, which we give to our customers, is the possibility to measure a real motor, for example, in another continent, to measure it in one of our test systems, generate a data set which can be then implemented in a different test environment to simulate the motor. So we call it digital twin. We can digitalize also real components and use those parameters inside a simulation model.
It just sounds amazing that we can do all of this in simulation without having to bolt a car together, drive it round the block, come back, download the data, talk to the engineers, make a tweak, do it again. We can do that all digitally. So how much time can we save by testing this way?
This, of course, depends on the component you are testing. In case of the inverter, definitely we have European customers reporting that they are able to save 90% of the time, because of course you remove a lot of mechanical components which takes a lot of time to be modified. And if you simulate those mechanical components, it is basically a mouse click. You can change those conditions. So in case of the inverter, the saving is in time massive. For other components, the saving is maybe smaller.
Okay. Well, time is not on our side. We've launched Inside EV Motors. We're spending money already. We're making payroll and developing our new electric car. And then all of a sudden, a regulator or a policymaker comes out with an even more ambitious set of emissions rules. Places like California and the EU have certainly upped or increased over the years their ambitions for EV adoption, and it goes in both ways really. EV adoption, promoting it, but also then penalising emissions, and particularly around CO2. So what are the impacts of emissions rules in places like California and the European Union, and what are the impacts on vehicle producers?
Well, with emissions, I've been in and around emissions testing, certification, and compliance the last 6 to 10 years. And I look at it now, and especially because I've recently done a Euro 7 combustion feasibility study where we were looking at what is it going to take to have an internal combustion engine actually be able to achieve the next generation of emissions legislation and, make a product that is ultimately marginally better in terms of emissions, but much more complex, have, increased costs in after treatment components and so forth. And the question becomes, is it really worth it? And whilst it's not explicitly written in the regs that you can't have an internal combustion engine, it's really forcing OEMs to examine how much electrification they have on their products and ultimately how many EVs they have. If I look at again, I'm going to use European examples here, fleet average CO2, you can start seeing a lot of the European manufacturers now. Some of them are having to play catch up because their products are producing, will have larger displacement, CO2 producing engines, and ultimately you have to offset that with a really strong EV lineup. And these days, it's just one of those things that the more complex the emissions legislation becomes, the more expensive the ICE solution looks like, and it just gets to a point where it's not feasible anymore. So we'll see how that happens in the next few years, but the whole shift seems to be straight towards EVs or something that has a net CO2 emissions at the tailpipe.
This is good news for our new car company because we can worry less about emissions testing, but I presume there must still be some regulations that we have to pass of some kind.
Well, for sure. And I mean, if you look at any one of your favorite EVs and the stickers that come out there, range is massively important, and same is power consumption. As I mentioned before, in watt hours per kilometer, those figures are highly important these days. At the same time, I think Luigi can walk us through it, but charging tests are going to become something that we see in the compliance sector in the next little while, and it's constantly evolving to adapt with how the technology is making it to market.
In case of charging, I had something. So today there are well-defined standards, as Nick mentioned, for the range and the consumption, but you recognize it also from the adverts, from the leaflets of the passenger cars, that every manufacturer declares the charging speed a bit differently. So, and there is ongoing activity at the standards bodies to create standards how to measure this charging speed, especially for what concern the fast charging or the high performance charging, in a way to have for the user more comparability, and also for the manufacturer to have the possibility to show how good is his design in allowing a fast charging of the vehicle. Because you mentioned before, with the 800 volt solution, we definitely go to have cars which will be charged in 10, maybe less minutes. And this is definitely a differentiator factor which has to be advertised by the manufacturer in a proper way.
Yep, and I think the final point I'll put on that whole topic is I think the way that we certify electric vehicles in the future, it's logical that it changes. If you think about driving an EV range test, for example, that's done in a test field called a chassis dyno. You actually have a human that sits there and will drive for 300 miles, in a stationary type environment where, he's just following a drive trace over and over again. And ultimately, there's going to be some variability in that cycle and so forth. And I think in the future, as we're getting so much more evolved in our means of testing, you're going to find an automated way of driving those certification tests. It also requires the authorities to accept what are standardized tire models, drive traces and so forth, but I think we can get more intuitive and more reproducible in our way that we certify in the future as well. It's going to be very interesting to see where we are 10 years from now.
Well, that is awesome. Guys, we've learned a lot once again today, and thank you so much for your time. And if we really were putting our fictional car company together, I know we would be in good hands with you guys. So thank you very much for your time today. Thanks a lot.
Thank you.
Thank you. My pleasure.
Thank you once again, guys. I invite you to check out the 5 previous episodes that we have in the series so far, looking at the race of various electrification technologies, how to simulate the ultimate EV, how you can use virtual environments, how you can look after battery safety and charging as well, all in the archive. Coming soon, we'll be talking fuel cells. But for now, please do check out our shows and your favourite podcast app, and now even on YouTube as well. Just search YouTube for Inside EVs US, and you'll find all the programs, the tech series that we are making with our partners at AVL. We're very grateful for their time and their input as we're all learning something about this exciting world of electric vehicles. Have a wonderful day. We'll catch you soon.